Dr. Simon is I was going to say river geomorphologist, a research geomorphologist presently with Cardno ENTRIX, which is an Australian-based company which operates all over the world. And I first worked with Dr. Simon in Mackay last year when we ran a river geomorphology short course looking at the physical and components of stream bank erosion. This sort of stuff is fundamental to river management, and the science of bank stability is really important to informing our management interventions on how we manage our rivers. And post for floods last year, obviously there's some major channel transformations and major gullying activities that happened in the Condamine catchment. What we're hoping to do as part of our Queensland Reconstruction Authority flood recovery efforts, which Condamine Alliance is involved in, is bring in some science to help us in managing a lot of that change in geomorphological structure of the rivers and the flood plains. And that is where Dr. Simon and his B-STEM model come in. So thank you everyone for coming. I hope that you get a lot out of this morning, and I'll hand it over to Andrew.
Thank you. Thank you for inviting me to do this. It's not very often I'm able to get an audience and talk about the type of work we're doing, and not only what we're doing, but why we're doing it. I do much prefer being called Andrew as opposed to Dr. Simon, so when we get into the question thing, let's do that way. What I'd like to do today is start talking to you about kind of the theoretical basis first for why streams adjust the way they do and the type of systematic response that streams go through, whether it's to floods or to destabilization by human intervention. And then go from the more theoretical into the applied aspects of how we can measure it, how we can model it, and for the most part to do this deterministically. And by that I mean looking at force and resistance and using then numerical tools to tell us if we know particular driving forces, how is the landscape going to respond? In other words, what is the resistance, what is the resiliency of the landscape to those processes? So just a little bit of background. I worked for 16 years for the U.S. Geological Survey in a series of places, Nashville, Tennessee, working on channelized streams out in West Tennessee, then to a place called the Cascades Volcano Observatory in 1990. This was a decade after the eruption of Mount St. Helens, and this was working on Mount St. Helens. And aside from working up in the Normandy, that was working on Mount St. Helens was for a geomorphologist, that's an unbelievable place to work. From there to North Carolina, working for the USGS. And then I left the USGS and went to the United States Department of Agriculture, a place called the National Sedimentation Lab in Oxford, Mississippi, which is where I am still. I'm in Oxford. And then about 6 months ago, I retired from the federal government and came to work for an American firm called ENTRIX, which then became an Australian firm called Cardno ENTRIX. And that firm is based out of Brisbane, and this is the second or third project we've had now working in Australia. One for Sydney Water, one for Australia Rivers Institute, and now up here with Condamine. So what I'm going to do is going to start just kind of waxing philosophical about river systems and disturbed streams, and this is why we're all here. I mean, we deal with unstable channel systems. Erosion and deposition is a natural process. It happens. Rivers are not static. They are dynamic. They shift around the landscape, but it's all about scale, and it's all about rates of change over time. So these are just some examples from North America, unstable channel systems. This is from Oklahoma in the upper left. Actually, all three of these on the left side are from Oklahoma. So you see gullies moving up into fields. You see head cuts. And then in the center is Mississippi, and you'll be seeing more pictures from there. It's about a 5-meter high bank. The channel has been incised, obviously, and then the banks have started to erode. You'll see this again. By the way, the drainage area for this thing is 2 square kilometers. Okay, so these are the type of issues we're dealing with in North America, and very similar to the issues here in Australia as well. So I always like to do this first when I'm giving a talk in Australia, because often I get the question is, why is an American over here doing work in Australia? And I always feel like I have to justify my existence and my place on the ground. So the question then becomes, are Australian conditions or rivers, are they unique? Are they different? And a lot of folks that I've talked to folks in academia, whether it's Gerald Nansen or Ian Rutherford or folks around, have this idea that Australian rivers are different than other rivers on the planet. And Gerald Nansen from Wollongong has written a fair bit about it. It is the world's driest continent, lowest and the flattest continent, and has the most variable flow regime. And in combination, these things can cause rivers to respond differently, and then maybe ultimately to have their morphology be somewhat different. So, prolonged tectonic stability, resistant bedrock in the uplands, therefore limiting sediment supply to some of these catchments, extensive unconfined low gradient plains, these are the conditions for many of the Australian rivers, no quaternary glaciation, which much of the rest of the planet has endured. The idea that rivers and the vegetation have evolved at the same time because of this stability, and that has some enormous effects when it comes to looking at the morphology, the shape, the width depth of channels, and the role that riparian vegetation can play. And this thing, the interdecadal precipitation variation, provides periods for establishment of this vegetation. That says the same thing. I should have taken that out. So the question then becomes at the bottom, right? So, okay, we have these different things about Australian conditions, but does that mean we have to do things differently, right? Because we have these different types of conditions. And no, and this is a soapbox of mine. And it's not only in Australia, but all throughout North America or wherever I'm given this kind of talk. No, the analyses are the same. And the reason is that the physics of erosion or deposition don't change no matter where you are. It's all about defining the driving forces and the resisting forces, okay? And the cliche being that gravity is a constant for the most part. So this is what I just said. The physics of erosion are the same wherever you go, no matter what hydrophysiographic province you're in, no matter what stream type, and that comes from a classification system in the US, stream type, by a guy named Dave Rosgen. But similarly, river styles, the Gary Brearley and Kurtz's framework for classifying rivers. We may be able to classify them differently. They may look differently, but they respond the same way. They will respond based on the driving forces and the resisting forces. So then it becomes simply a matter of defining those driving and resisting forces. And we get channel adjustment when we have an imbalance between those forces, right? If we have too much driving force relative to the amount of sediment coming downstream, we're going to have an excess amount of energy and the channel is going to start to change. So, in terms of defining why rivers look different, we're talking about the difference in the rates and magnitudes of adjustment, which are related to sediment transport, and then ultimately that's going to determine a stable channel form. Okay, so this equation has been attributed to an engineer named Lane in the 50s, but it really dates back earlier to Carl Grove Gilbert, one of the foremost geomorphologists, hydraulic engineers of the early 20th century. It's not an equation, it's not used for prediction, it's a proportionality. And basically, on the left side, we have the unit weight of water, we have discharge, and let's think of it as kind of a bankful discharge, times slope, okay? So what do we have there? Power. We have stream power. This is total stream power. And all this is saying is that total stream power is proportional to Q sub S, which is the amount of bed material that can be transported by that flow, times the size of that bed material, okay? Stable streams, quote unquote, operate in this balance. Again, stable streams are not static. There's always transport, there's erosion, there's deposition, but they will vary about some mean condition. So let's imagine as human beings we're on the landscape and we do something to disrupt this process. All right, say we channelize a stream. Okay, so we have a nice meandering stream, well maybe not so nice, but we have a meandering stream. We dredge it, we channelize it, what do? We increase the slope, we increase the amount of discharge it can handle, because we're not losing energy on the outside bends. So what happens? We have greater stream power. The channel is going to start to erode. That's going to, initially, if it can, take it from the stream bed. So it's going to do that until it gets this up into a balance again. Okay? So let's take another example. We clear grasslands, we clear forests, and we build parking lots and shopping malls and highways and stuff like that. Water doesn't infiltrate into the ground anymore, it runs off. We have greater runoff rates for unit precipitation, so we increase Q, right? So we get incision, even though we've done nothing to the channel. Okay, so this is an indirect response. One more example. We build a dam, okay? We build a dam. Now, on the upstream side of the dam, all the hydraulically controlled sediment, the sands, the gravels, are trapped, right? So now, let's assume that gamma QS stays the same, although we know it doesn't in a dam, so we build a dam. But now we've cut off the upstream supply of sediment. What happens? The channel is going to incise. So again, this is a great conceptual framework to think about how what we do on the landscape or what we do in channel systems affects the channel down the road. And this is kind of what happens. The upper two plots are following channelization. These are some examples from West Tennessee. And what you're looking at there is, on the y-axis is bed elevation, on the x-axis is time. So we're looking from 1996. That's wrong. That should be 1966. Okay, I've showed that slide 100 times, and that's the first time I've seen that. Okay. Appreciate it. Yeah, so it's a non-linear response. What happens when there's initially a disturbance, right? The magnitude of that difference between the driving forces and the amount of sediment is large. Channel starts adjusting. As it does, the slope is reduced. So that difference gets smaller and smaller. So that process attenuates. This is from USGS professional paper by Reds Wallman and Gar Williams. This is the incision downstream from dams throughout the U.S. Okay, so same kind of thing. We've created that imbalance. So examples from the Arno River in Italy, some work I did with a guy named Massimo Rinaldi from the University of Florence. And we're looking at two phases of, Massimo was able to identify two phases of degradation. The first one, between 1900 and around 1940. And basically, there were land use changes that reduced the upstream supply of sediment to the river. And what did the Italians do? They started planting forests again in the uplands. I mean, that's a conservation measure, right? But we reduced the supply of coarse sediment to the stream, so the Arno started incising. Following World War II, Italy had to rebuild. Where did they get the gravels from? They got it from the rivers. Okay? They also built dams, so they cut off the upstream sediment supply. They dredged it out, so they had all these nick points moving up through the Arno, and you can see the size of the amount of degradation. So again, we're moving on across different continents. Now I'm going to show you I'm going to compare two very different fluvial systems. They're both in the U.S. I apologize. By the way, I live about there. So this is the central U.S. What is shaded in gray is, or I guess that's brown, is the loess area of the Midwestern United States. Loess is that silty material on the front end of the wind-blown sediments that were deposited from the outwash plains of glaciers. And they behave much like the sediments you have out here in Condamine. So, very erodible soils when they get wet. This is what the channels look like. This is the disturbance. The U.S. Army Corps of Engineers and their infinite wisdom, and the Soil Conservation Service, quote unquote, and local drainage districts started channelizing streams, because what happened is that after European settlement, much like here in Australia, landscape was cleared of forests and grasslands, everything went into agriculture, runoff rates were changed, they channelized, material that was eroded from these upland areas filled the channels, okay? So the farmers that were working the bottomlands couldn't farm their lands, water was getting up and out and staying out for long periods of time, so they channelized these streams, much like the British did in India, to drain this water off the landscape. So what happens? We have a downstream disturbance because they channelized from the mouth of the stream, moving on up. It was anthropogenic. And in this system, it's sand bed, so highly mobile sediments, and a cohesive bank system. Okay? So if we think about the stream power proportionality, what do we do there? Well, we have a great increase in transport capacity, right? We have a bigger channel, we have greater runoff rates, and we have a great increase in slope because we channelized it. And this is kind of what it looked like. These are the responses. So Mississippi, Tennessee, Nebraska. You may want to count the number of times you see this slide during this talk. I think it's 8. And you can barely see it, but there's a car down here. We call this Mississippi riprap. But basically what's happened here, the channel incised, the bank started widening, and the head cuts just moved up as far as this box culvert until that gets undermined. So that's one example that we're going to look at. We are going to compare the response of that system to Mount St. Helens. Okay, coastal plain system, alpine system, completely different environment. So here we are up in the Pacific Northwest, Mount St. Helens in Southwest Washington, May 18th, 1980, 2.3 cubic kilometers, blew off the top of the mountain. There was a huge debris flow, came down. You can see the map of the North Fork Toutle River. Here's a person for scale on the Toutle. You can see the depth of the lahars, which are volcanic-induced mud flows that came down. Basically, so it transformed this beautiful trout, gravel, cobble stream to something that looked like this, all right? So, what was the disturbance? If we think of it just in terms of this stream power proportionality, we had an upstream disturbance here, not a downstream one. It was natural. In a coarse-grained, non-cohesive bank system, in other words, sand and gravel system, so we now have an increase in transport capacity, okay, because when the debris avalanche slid off the top of the mountain, it basically buried the North Fork Toutle system. It was gone. There was no surface drainage left, to a depth of almost 100 meters. So it's a natural laboratory, right? So we had no stream system, and the rivers had to recreate themselves. So we had a huge increase in transport capacity. We also had a decrease, though, in the resistance of the material for transport. Went from a gravel cobble stream to like a silty, sandy stream. And so if we look at the response, these are photos from the USGS. These are the hummock deposits from the debris avalanche that had come down. The channels have cut through. And we see a lot of the similar things. We see incision, we see widening, and then we see meandering through this system. So I'm going to dare to compare these two systems. So, and we published this in 1992. God, that's a long time ago. It's 20 years. Okay. So Mount St. Helens on the top. The numbers aren't really important, but in the upstream reaches, you see this nonlinear rate of erosion. Of course, that's a regression. Nothing happens that smoothly. You can see how it varies about that. But even though we had additional eruptions in '82, we had additional mud flows, we had additional lahars coming down, it still continued to operate according to the initial disturbance. In the downstream reaches, all the sediment's coming, starts filling in immediately. That's Mount St. Helens. This is West Tennessee. Again, a completely different environment. So here in this example, channel incises, okay, because it has all the excess energy. You can imagine that the slope is being reduced. So now it's flatter. Meanwhile, this disturbance is migrated upstream, okay? So we have less stream power now in this reach. Now we have all this accelerated amount of sediment coming down. The reach where we're at, it can't transport that anymore. So it starts to fill, okay? Okay, so what we did was we tried to compare these two systems. So here's Mount St. Helens and North Fork Toutle. Here's West Tennessee. So what we have on these plots, the y-axis is referred to as the A value. So what does that mean? So if we erode over time, okay, and we consider that the elevation at time 0 is 1, okay, so it's dimensionless. If the channels are grading, it's going to be dimensionless elevation, so it's almost like a percent. So it'll be maybe the ultimate elevation might be 1.1 or 1.02, where if we're losing elevation, it's going to be 0.99, 0.98, 0.97 of the original elevation. Okay, everybody follow? So what we did is we had these, we had the data for how the channel was changing, the elevation was changing over time, all right? Push those regressions out to where they became asymptotic and grab that point, okay? That was the A value, which then we plotted. So for the North Fork Toutle, we have the lowest A value at the point of maximum disturbance, which was at the toe of that debris avalanche. So you can see it's about 0.9. Downstream, we're all above 1, meaning the channel's filling, okay? And then basically attenuates with distance upstream, okay, as we move away from that initial disturbance. Well, here's West Tennessee, completely different disturbance, completely different environment. These plots, you can almost overlay them. You have the point of maximum disturbance, which is the upstream end of the channelization work. The erosion process migrates upstream, attenuates, deposition downstream. These points represent the secondary response. So you got that initial degradation, and then you have filling coming in. If we plot enough of these over time, you'll find it kind of all links up in a linear way. So these are two different systems. So you have the North Fork Toutle and the Obion. And fundamentally, in terms of vertical changes, they've responded exactly the same way. Okay, so now I've taken that plot, this is the North Fork Toutle, and I've just kind of sketched that in. You can think of that as almost like the volume of erosion that has come out of the channel bed, all right? Now I've plotted that again, for the Turbulence River system as a whole, and just ignore the black ones, the black dots, that's the secondary response. So we're looking at, don't touch the screen, the open circles. So if you look at this, and that's the amount of erosion that has come out of the bed. That's the amount of material that's been deposited. And in most cases, in most analyses, whether folks are doing geomorphic analyses for just a research study or whether they're doing applied research and actually having to put something on the ground, this is as far as they go. Models like HECRAS, industry standard for 1D sediment transport and morphodynamic change, that's what it does. It does the bed, period. Okay, now hold that thought. So if we have this much coming off the bed and this much being deposited, and we know ahead of time from other studies that the amount of sediment coming off the hill slopes basically was done in the first couple of years, okay? Where's the rest of that material coming from? The banks. And most people ignore the banks. And it's been something we've been just banging home for almost 20 years now, okay? So if we look at widening then, let's compare the two systems. So there's the Turbulence River system on top, and I caution you, that's on the y-axis, that's 5 log cycles, okay? This is not for prediction, just to give you a handle. But if we would try to draw a line across there to come up with an average, maybe for the two, we're looking at 10, 20 meters per year. Meters per year. When we first started working in the Alliance system, where I was working in the early 80s, we saw widening rates about anywhere between half a meter and a meter on average. That's a dynamic system. I mean, that's moving around. Then we get out to St. Helens, it's an order of magnitude greater. So why are they different? We saw that the trends of response in bed elevations were relatively the same, but why is the widening rates different? Resistance, force and resistance. The Turbulence River system, sand and gravel, no cohesion, easy to erode. The Alliance River system, cohesive. Okay, we're going to come back to that. So from what we've learned so far about how channels respond, okay, so they incise, they widen. We put together, everyone has to have a classification scheme, right? Well, this is mine, okay? Mine and Cliff Hop, this is from 1986. So we think of it in terms that we have a stable channel. And what do we mean by a stable channel? It's not static, it erodes sometimes, it deposits sometimes, but there's no trend of erosion or deposition over time. This is the definition of a graded stream, which dates back to the Hoover-Mackin from the 1940s. Okay. So that's stage one. Maybe the only places we have these now are in national parks and places like that, because human beings have made a huge impact on the landscape. So, what does a stable channel mean? It means overall, all the sediment that's being delivered from upstream is being transported through that reach without additional incision or widening or narrowing or filling. It's not to say that there's not scour and fill on a hydrograph. Okay. Vegetation may extend down to the low flow line. And actually, what we saw on the Condamine, even though it took the hit from these huge floods, huge trees still in there, low down on the banks, indicating that it's a relatively stable stream. Okay, stage one. Stage two is this disturbance stage. It could be actually some human beings getting in there and dredging or channelizing, or it could be some disturbance that was done up in the watershed. It basically signifies that something has been done to disrupt this balance. So then we'll get degradation because we have this excess amount of energy. Ultimately, the banks will get high enough that they start failing by geotechnical forces. So again, what we so commonly see is that when someone even dares to analyze stream banks, they'll do it in terms of only stream power or only shear stress. And that's only one of the two processes that are important in terms of stream bank erosion. And we'll get into that some more. So banks start widening as the channel widens out, right? It starts reducing the depth of the flow, reducing the shear stress. Our disturbance has moved upstream. We now start getting deposition on the bed and the low bank surfaces. Widening is still going on because the banks are high enough. The cool thing is that you can go out there in the field and you can observe these processes by going on, by looking at the channel, by looking where the vegetation is coming back in, by seeing if vegetation, vegetation puts out a root flare, it will look buried. It'll look like a telephone pole or something like that. Now, in the US or in North America or Europe, we can go in there, dig down to the root collar to find a germination point, core the tree, count the annual rings, and we can get a rate of deposition. And if you do that enough over enough areas, you can actually you can understand rates of processes. Ultimately, the bed will come up enough that the banks will lay back through failures that that they'll become stable. This is very typical. This is a two-stage, kind of two-tiered channel. And when we start talking about rehabilitation and restoration, I know in North America, everybody wants to go back to there. They want to go back to stage one. They want it the way it looked like when the Native Americans were running around, when Lewis and Clark were out exploring. In most cases, we're not getting back there. We cannot get there from here. Because our channels look like this. We've changed rainfall runoff relations. Human beings are on this planet, for better or for worse, and we've had huge impacts. So when we see these type of things, we have terraces. That's no longer a floodplain, right? So, not for engineering design. But what we do with this is that we use this as a reconnaissance tool. We can do this on the ground out of a truck, we can float it in a canoe, we can do it out of a helicopter. And we just get stage of channel evolution. And what it does, it indicates to us whether we have a disturbance which is localized, or system-wide, okay? And because there are very different treatments for those two differences. Okay. We're doing okay? So far we've been talking about this kind of semi-quantitative empirical look. We have the stream power proportionality, which tells us, yeah, the channel is going to be unstable. Do we know how it's going to respond? No, we just know it's going to respond. Because it's going to be a function not only of those driving forces, but of resistance, all right? And so that's all that proportionality provides us with. So the second one is that similar channels, okay, geometrically they may look exactly the same. You impose the same disturbance on them, they may respond completely different. And in an applied sense, right, when we're talking about restoration or stabilization, that's the question, right? If we disturb it, if a big flood comes through, how is it going to respond? In the US, this guy, Dave Rosgen, uses this form-based process and basically says, I want the channel to look like that. And they just built it like that. Immaterial of what's going on upstream, what's going on downstream, and totally independent of history, of time in response. Because if we know we have a stream, because we don't restore, we don't stabilize stable streams. We restore those that are unstable. So we need to know where we are in that adjustment sequence. If we're talking about putting in bank stabilization works and the channel is still incising, they're not going to stay there. You're going to be throwing your money out. We have to know where we are. Okay, kind of a theoretical thing here. So if we think about the stream power proportionality and how this channel operates in nonlinear fashions, the top part of that graph represents the driving forces. And we see that over time we have nonlinear response. So we're starting with shear stress, right? Boundary shear stress, unit weight of water, times the depth of flow, times the slope. Unit stream power, total stream power, or this one, SLB is energy slope, okay? And over time we know that these things should attenuate over time. And that's all we generally look at. We don't think about this, what's happening with resistance. Now at St. Helens, granted that's a special case, we had mixed sediments, all the fine stuff got washed out first, so resistance was increasing over time as well, okay? But even in where you only have one kind of sediment, as streams stabilize, as you have vegetation coming back in, roughness increases, right? So that same shear stress is not going to be having the same effect on the boundary as it would before. So it's a question again of knowing where you are, and your management options are going to be very different depending where you are in here. All right? If you're out here, yeah, you can start doing bank stabilization work, maybe even here. But here you better put grade control in, right? Because the bed is still moving. Okay, Cyril and I talked about this yesterday, and actually Mark and I talked about this also. It just always seems to be popping up. Energy. And it's another cliche. When you're doing restoration, it's all about energy management. It's about managing the energy of that flow. You have an outside bank that's failing, you want to roughen up that surface, you want to slow the flow down, smooth the other side, let the river do the work. Okay. So, theories that came out, I think it was in the 70s, Howard Chang and Ted Yang, suggest that, or indicated that, channels adjust so that they dissipate a minimum amount of energy over time. Okay? Corollary to that is that a given flow, or that channels adjust so they can transport the most sediment for a minimum amount of energy. So if this holds true, we should be able to track this over time. Okay? Because the original theories just said, you're here, but when you get down there, that channel is going to have a morphology such that it's dissipating minimum energy. So I said, well, okay, we're working in West Tennessee, we're working in Mount St. Helens, we have a good data set, let's see if it actually works. So, Bernoulli equation, right, it's from our intro to hydraulic engineering. Energy of a flow on the left is Z, the datum head, plus the flow depth, plus the velocity head. Okay, so we have energy at point 1. We go down to point 2. Now Einstein told us that energy is neither created nor destroyed, but hey, we have less energy down here. Where'd it go? Okay, well, it goes to friction. They say it goes to heat. I've often wanted to just put some thermometers in and see if you actually do lose that. But
What about noise?
what about what?
Noise.
Noise?
Dissipation of energy through noise.
You mean like turbulence? Yeah, sure.
Can you put it on there, please?
No? It's in that term,
Yeah.
right? I'm touching again. No touching. Okay. That's a good question. Yeah, it's turbulence, basically.
Yeah, Calvin says about 80% is lost through heat and noise.
Yeah, but the noise is turbulence.
Yeah,
Yeah.
I realise that.
We good?
We're on the same.
I think we're on the same page, sir.
Yeah.
Yep, okay. All right. We spent a day in the field together yesterday. It was awesome. Okay. So let's think about energy and how the components of the energy equation would result in a minimization of energy. So let's take the datum component. How are we going to minimize energy? We're going to incise the channel, right? We're going to give us a lower elevation. What about flow depth? Widening, widening, widening. As the channel widens out, depth gets shallower, shear stress goes down for the same slope. Aggradation also. Filling will give you a reduction in energy in terms of flow depth. Because unless the channel is vertical, right, as that bed comes up, the same discharge is going to now have a wider cross section. Then the velocity head widening again, because again the flow gets shallower, we'll have an increase in roughness, vegetation, aggradation. So what this is telling us is that it's not necessarily the same processes that are going to reduce energy. We've got degradation and aggradation, both resulting in a loss of energy. And you'll see widening showing up a few times. So let's take a look over time. So here's the energy slope. It's the North Fork Tula River. 2 examples here. This is boundary shear stress, which is really what's telling us about what the channel can transport. This is a grading and widening. Those are degrading and widening. Completely opposite processes. They're both minimizing energy. Let's look at unit stream power. So now we have West Tennessee degrading streams, Mount St. Helens degrading streams, and then aggrading streams. So they're completely different environments, different processes, but we're still working at minimizing energy over time. And the result of that, as we minimize energy, we minimize the ability to transport sediment. Because this is some data over the first 12 years after the eruption of Mount St. Helens. That's in millions of tons of sediment, okay? All right, so what that means is that, so we adjust a channel, do we still know how the channel is going to adjust? All we know is that there's an excess amount of energy, it's going to minimize its energy, okay? So that's the theory that holds it all together. But how are they going to do it? So we put this together and published this, I don't know, quite a while ago. The y-axis, if you think of it as a dynamic width-depth ratio, okay? So in other words, what's the change in width relative to the change in depth over the course of an adjustment? And on the x-axis, we have the disturbed channel gradient, okay? So we're going from point 0001 all the way up to a 10% slope here, all right? So we'll start out, and we can use this axis as kind of a surrogate for the environment that you're in, or the physiographic province. So the low slopes are going to be the coastal plain areas, probably going to have silt clay bed and banks. And we see that when the channel adjusts, the width is going to change about 6 to 10 times as much as the depth. We get into steeper environments, we're going to get into coarser sediments. No cohesion on the banks. So when we disturb that channel, we're going to look up almost to about 100 times the change in width relative to the change in depth. So we're getting there, but we're getting there completely differently. And then when you go even steeper, you may have bedrock along the walls of the channel. You may have more resistant material. So again, it comes down. Again, I caution you, 1, 2, 3 log cycles here, 3 log cycles here. This is not for prediction. This is just for a conceptual understanding that these systems, once disturbed, will respond differently as a function of the boundary. So we did a little numerical experiment with a guy named Steve Darby, who was a postdoc at the National Sedimentation Lab, now at the University of Southampton, editor of Earth Surface Processes and Landforms. And Steve was, for his PhD, did the first kind of model where he linked flow and sediment transport with a very simple bank stability model. Okay, so now we're finally, this is the first time we're able to bring both the vertical processes and the lateral processes in together. So the question is, let's start with a channel where we know the stream power proportionality is balanced, it's all good, we're happy. How does that channel respond if it's disturbed? Will it size, what's going to happen? And if the bank materials are different, will we stabilize to the same geometry? This only provides us with little insight. We know if we have excess energy, it will erode. We just don't know how much, or we don't know where. Okay? And we use this numerical model that Steve put together a number of years ago, quite a number of years ago. Okay, so how do we disturb the channel? Again, this is a numerical simulation, so we're not actually going out and disturbing the channel. We basically took the transport capacity of the flow, and we just cut off half of that upstream sediment supply. Okay, so that gets back to the stream power proportionality. Cut off the sediment supply, we're going to erode something. We're going to erode the bed, the bank, something. So the initial slope was 0.005, and initial width depth ratio was 13.5. It was a sand bed channel, and so we see the bed material is all the same, 1 millimeter of sand. Well, all we did was change the composition of the banks. That's it. Everything else is the same. So for the sand channel, this really should have been about 0.5 or 1, but we were naive at the time, so it was at 4. For clay bank, we set the cohesion so high, we knew the banks would not erode. Okay, basically fixing them in place. Friction angle of the bank material, and then the sand content of the banks. Okay, and then we cut it loose. So I know this is a lousy looking plot, but just look at, I will walk you through it, but look at only the open circles. Okay, so you'll see, here's dimensionless energy slope. So we disturbed this channel, right? The sand bed channel of clay, silt, and sandbags, they basically all responded to about the same amount of energy dissipation. Slightly different, maybe 1 or 2% different. The question is, how did they get there? And really, the reason we brought this back, this part of the lecture back, is to literally fight against the folks in North America that are using this kind of cookie cutter approach to restore streams. This kind of classification-based thing, this form-based thing. To say, if you go out with a channel, because their system is based on a given geometry. So this channel is what they call a C5 channel. What does that mean to you? Nothing. What does it mean to me? Nothing. Okay? It basically defines the shape of a channel, okay, and the slope. Okay? But they think that they can then design a channel based on knowing it's a C5 and where what they want it to be a B4 or whatever. Okay. So for each of these channels, how did they respond? I want to make sure I'm doing this right. Okay. So the clay bank channel, I told you the banks are fixed. So the elevation, the dimensionless elevation adjusts to about 0.96 of the original elevation. The silt bank channel to about 0.97. The clay channel to about 0.998. I mean, and even at lower slopes, which is what these other curves are, the sandbank channel is filling. It's not even eroding. Why are they different? The clay bank channel didn't change its banks at all. The silt channel eroded its bed. Finally, the banks became unstable and then started widening. The sandbank channel started widening immediately because of the very low resistance of the materials. So here are the answers. Let's look down that left column. So in the clay bank channel, we had 3.5 meters of degradation, down to an order of magnitude less in the sandbank channel. Just a completely different response. Same disturbance, all we changed was the boundary materials. Widening 0 up to 13 meters. And the bottom line for stream restoration, the engineers that actually have to put this stuff on the ground, is that what's the ultimate stable width depth ratio, right? That's what you have the contractor out there building. Well, it ranges from about 5.5 up to over 16. And that kind of uncertainty is just not good enough for engineering design. You're going to get it wrong. So again, this is the idea of using this deterministic approach. How do we apply this to restoration? Okay. There are numerous approaches. We can use an empirical thing, regime equations, kind of like, the hydraulic geometry equations, like width, they're all power functions. Width is a function of discharge, depth is a function of discharge. But that's still, it's empirical. It doesn't really give you the feel for or the understanding of, because if we use a regime equation, it wouldn't have worked in that previous example, unless we knew the resistance of the banks. Obviously, I am a proponent of the deterministic, physically based approach. It's no more expensive than the empirical approach. To do the classification schemes or to go out there, you still have to collect field data. But why not collect the field data that you need to parameterize the processes that are actually changing the channel? Because if you can do that, if you can define force and resistance, then you're good. You should be good to go. Okay? So, it's a big toolbox. Use what's appropriate for the scale and objective. And that's a big deal also. Are we looking at a localized problem? Maybe we have a constriction at a bridge or a deflected flow, or we have cattle coming in and eroding the bank. Well, yeah, then maybe one of these classification scheme approaches would work. You'd say, okay, it looks like that upstream. Looks pretty good. That looks like that upstream. Let's build the same thing in the middle. I get that. But more often than not, we are dealing with the instability of entire fluvial systems, and we have to know where we are in that process. Okay, so here's an example, and I already gave you part of the answer to this because I'm going to ask you a question that is pretty much rhetorical. So here's an unstable reach. The way the classification schemes work in terms of restoration, they say, right, that's our channel that we need to restore. Let's go find a reference reach, all right? Let's find a stable analog, maybe in the same channel, maybe in the adjacent watershed. All right, so we found one. There it is, okay? Now my question to you, and you have no way of answering this, but it's fun for me anyway, is how far apart do you think these are? And I'm telling you they are on the same channel.
2 kilometers.
Okay, that's good. Someone actually gave an answer. It's like 50 meters. There is a supercritical flume stream gauging station in between these two sides. Basically, I'm standing on a bridge, and I'm pointing downstream, and I'm basically rotating and then shooting upstream. Okay? So basically, we had a disturbance migrate up through this channel, right? And it was stopped by the road and the concrete structure. To build that over there, I mean, you're talking about, those banks probably 8 meters high, 50, well, there's Roger in the bottom of it. But you can't do it. You can't get there from here, okay, using an empirical approach. It's 100 meters, I lied. Okay. So what we like to use is this kind of tiered approach. First thing is the reconnaissance level. And we go out and we do what we call these rapid geomorphic assessments. And everybody has their own way of doing it. We do it our way. And it's basically going out and using that stage of channel evolution, basically looking at channel form, but we really don't care what the size is. We don't spend time measuring it because we're really ultimately, unless we're going to analyze that data intensively, we don't need to know that. We need to look at form and infer process from it. So do we see falling trees in? Do we see the banks failing? That's going to tell us what? Banks are too high, they're unstable, okay? Do we see, for instance, tree roots exposed, but the bank's still stable? Well, maybe the channel is just degrading and it's just scouring out, and the banks are not high enough yet to actually start failing. Or if we see vegetation that's been buried, aha, we have an excess amount of sediment coming. It's telling us something about the dynamics of the system. Again, the reconnaissance approach is not for design. It's just to give you a handle on what are the dominant processes, to get you on the ground and to figure out what's important. And the idea is identify the problem, not the symptom. You go out to the channel, the banks are failing. That's the symptom, right? Now, if it's a localized disturbance, all right, then we could deal with that. But if it's system-wide, we need to know what the problem was. If we put in bank stabilization, is the next wave going to cause more degradation? Okay, so here's an example of just using a reconnaissance approach. Apologize, this is North America. This is near the Four Corners region, Colorado, New Mexico, Arizona. Beautiful part of the country if you've never been there, Red Rock country. So, we're doing this piece of work for the New Mexico Department of the Environment. What they had, this is related to the Clean Water Act in the US. This stream reach was listed as impaired due to sediment deposition, okay? It's supposed to be a warm water fishery. There's a whole story behind that too. Upstream, the Corps of Engineers built Navajo Dam. And in America, everybody loves to blame things. We're being taped. I've got to be careful with this. But we do love to blame things on the Army Corps. It's just what we do. All right? And so I had this preconceived notion. You go out, we got a channel with erosion problems downstream from a dam. It's the Corps. You know, it's because of the dam. We had incision. We had bank widening. All right. This is the value of getting on the ground and not relying on Landsat imagery. Okay. So you get out there. The green dots represent stage 6, stable stream. Okay? The reds represent a stage 5, so filling and widening. And then, well, the other colors, we'll just leave those go for now. So we come downstream in our canoe. About here is a world-class trout fishery. People fly from all over the planet to go fishing here. It doesn't look impaired to me. Now, the funny part of the story is that it's listed as impaired because the water coming out of the bottom of the dam is cold, right? So it's a great cold water fishery, but this stream is listed to be supposed to be a warm water fishery. That's, you know, that's state law. I'm not going to go there. Be that as it may, green, 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 stable, 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 all the way to here, right? From here on down on the main stem of the San Juan River, all of a sudden, huge amounts of sediment coming from. We haven't analyzed anything. We're just observing, taking photos. Canyon Largo here is the largest arroyo system in the southwestern United States. I live in Mississippi, I didn't know that, okay? So, it's like huge. Arroyos, gullies, you know, the same kind of thing. Pushing out huge amounts of sediment. So the bottom line was that the problem with all this deposition had nothing to do with the dam. It was all coming out of Canyon Largo. Okay, so that's the kind of information you can get from just doing these rapid geomorphic assessments. Okay. So I said this earlier, if the problem is localized, you have a lot more options. Okay, you can even use these kind of very empirical, very form-based approaches. But you can just as easily use a deterministic approach. Okay, if the problem is system-wide, then you have bigger issues, right? You have to know where you are in that adjustment sequence. We have to understand how much things have been adjusting over time, where we are in that non-linear adjustment process. And the key is the resistance of the boundary materials. We have to know how strong they are to resist flow and to resist gravity. So in that case, we need to rely on validated, there's no way, scientifically vetted numerical models. Lucy tells me I have 10 minutes. I told her no way. But she is the boss. So, okay, so this is what we call the analytic level. There's static and dynamic numerical modeling. You can go in like we can with the bank stability modeling. We can just say, right, here are the conditions, here's the resistance, here are the flows that are going to come through. Can we model the amount of erosion that's going to occur under existing conditions, and a whole shopping list of mitigation measures. The other thing is to start routing flow and sediment, okay? Because that's really what it's all about. Now, we can't extract the channel system from the landscape system, because we saw from the work that Massimo Rinaldi did on the Arno that we had an unstable channel, even though nobody did anything to the channel. It's because the Italians started planting trees in the uplands. That destabilized the channel. Where we're at, and it's it's here in Australia, it's in North America, we've been fighting this battle for 20 years, is that most of the watershed models treat the channels either as pipes, okay, as just conduits for sediment, or some very simplistic way of looking at how the channels are adjusting, okay? So the key is ultimately we have to know what the sediment contribution is coming from the uplands if we're going to get the channel modeling right. So what do we do with regard to channel modelings where we are? We have our bank model, and I'll talk to you a little bit at rapid speed. These are the type of things you can handle. It is not a sediment routing model. My son works with high-performance computers for NASA. He thinks of it as a toy, okay? It's basically a spreadsheet tool. But now, we're working on bringing it into the industry standard HEC-RAS. Remember I was teasing HEC-RAS, that it only gave you vertical changes? Because of the example I showed you, the modeling example from Darby, the results coming out of HEC-RAS, if you have mobile banks, are completely biased, right? Because it's going to have to take all that energy out vertically, okay? So we're merging these two models, that's ongoing. We're also working with the U.S. Bureau of Reclamation, their Denver research office, to merge the bank model with their two-dimensional flow and transport model, okay? This is the bank model, and originally when I came out here thinking that we're going to do this thing Friday, I thought this is what we're going to talk about all day, or at least, yeah, all day. It is a purely process-based model. It handles this whole host of things. It is completely deterministic. There are no knobs to tweak, okay? And the bottom line is that we can collect all the data we need, which we have done over the last 2 weeks here in the Condamine Basin, in a day at a site. That's a maximum, about a day or half a day. So, bank stability processes. Pretty typical shape, huh? In an incised channel, we have that vertical face. We have hydraulic erosion. Remember I said bank erosion is 2 processes. So we have hydraulic erosion. This is the first one, so we get the hydraulic processes, undercutting the bank, we get a tension crack developing, and in your soils here, you do get tension cracks developing. Infiltration, and then raise the pore water pressure, and these are all the processes that we have to include within in the model. Because the pore water pressure is going to reduce the strength of the banks. So the resistance is not constant, it changes. Shearing starts, it goes, materials deposit at the toe. It may deposit as blocks, it may deposit completely, may not deposit at all, may just drop into the flow as dispersed aggregates and on downstream. But you notice when it fails very often, it'll fail back at a flatter angle. Okay? It won't continue to keep failing if you can protect the toe. So toe protection is key in bank stabilization work. And then hydraulic erosion, and we'll continue to remove it. And there you go, and that cycle keeps going on. So bank stability is decreased by soil moisture, the weight, and then generation of pore water pressures. Toe erosion, which increases the downslope driving forces, increased by vegetation, root reinforcement, if a failure plane has to slice through those roots, and evapotranspiration. It's huge in what it does to help lower the water table and increase the strength of the banks. We don't have a lot of time to talk about that today. Drainage, anything to get to lower pore water pressures, and rugby balls. Anything, if you put a rugby ball to toe your bank, you'll be able, you know what I mean. I never get a laugh on that anymore. All right, so the way we analyze this is with the factor of safety. Okay, the factor of safety is resisting forces over driving forces. See, so the geotech guys had this right a long time ago. It just took us geomorphologists a long time to realize we have to analyze things the same way. So, at a factor of safety of 1, that means resisting forces exactly equal to driving forces, theoretically, and the bank should fail. So let me show you, this is just an example, but it's really instructive. So we're running at about, this is from 97 up through 98, it's in Mississippi, and we're running at a factor of safety of about 1.2, so we have 20% more resisting forces than we do driving forces. And you see it's getting greater. It's getting greater why? It hasn't rained. It's dry. We're getting greater matrix suction in the banks. The resistance is increasing. Well, then we get a reasonable peak, right? We get lateral infiltration, the bank wets up. We lose some strength. Does the bank fail? No, not yet. Because it's lost a lot of its strength, but it's still not unstable. Well, we get another event, right? It drops a little more, dries out. And then finally, it's like this 5th event, and it's only a moderate event, that is like the straw that broke the camel's back. Okay? Bank erosion is not a linear process. The hydraulic erosion is, you can relate that to discharge or shear stress. But bank failure is due to the geotechnical properties. Okay? And then you see as it dries out, the factor of safety just increases again. So this is kind of example output. So here's an event we might have modeled in B-stem. And then we use an example of say, okay, what happens? We'll output that, the toe erosion, we have a bank full event. We'll then output that into the stability algorithm and take a look at what happens if we leave the water table up here. This is the drawdown case and the surface water in the channel. And then it'll give us, and it'll predict under what conditions the banks will fail. So what we can do is when we're looking at restoration activity, we can say, right, instead of silt at the toe, well, maybe we have rock now. So instead of a resistance of 5 pascals, maybe we have 250. So it's not going to cause that much undercutting. And the same with adding vegetation or battering the banks back. I thought I'd give an example from, well, let me stop here for a second. I haven't nearly gotten to the end. And I'm going to ask the group. Obviously, we're running out of time. Do we have more time for me to chat, or do we want to break into questions, or what do you think?
We've got 30 minutes until we break for lunch.
Okay.
So,
What does everybody think? I'd kind of like to keep moving through, if that's okay.
Finish the story, Dad.
Finish the story. Roger that. Okay. So, and I have to do this because it's an Australian example. So there's some work I was doing with Andrew Brooks from Griffith University. Has to do with, sediment delivery to the reef, the coral sea. Gorgeous, right? So the O'Connell is a typical agricultural watershed draining to the reef up by Mackay, and it's reported by Brody and others as having the highest sediment yield, so the highest amount of sediment per unit area being delivered to the Coral Sea from all the reef catchments. Okay, so here's the data, about 750,000 tons per year. You can see how the O'Connell compares with the Fitzroy and the Burdekin and the Normandy, where Andrew is working. But look how small it is. It's a teeny watershed compared to the Burdekin and the Fitzroy. Yet it's 750,000 metric tons per year. When we look at that in terms of sediment yield, okay, so sediment per unit area, you can see where the O'Connell pops out, both in terms of existing conditions and under quote-unquote natural conditions. So it's, according to this report, highest yielding sediment in the reef catchments. Okay, so there's the O'Connell. This is what it looks like on the ground. This is the reach we're working in the upper left. We did kind of those RGAs up and around the basin, kind of observing, and we didn't see a lot of erosion off the slopes. We didn't actually see much bank erosion either, to tell you the truth. And about 5% we estimated of the total length of the banks, okay, were producing sediment. Okay, so there we are. There's Mackay, and there's Mackay, and that's where the O'Connell is. So, when we're talking about bank protection, we have to talk about the difference between protecting against hydraulic versus geotech processes, because they're very different, right? So, hydraulic protection means either reducing the available shear stress, somehow, or increasing the resistance. Geotechnically, we're talking about either increasing the shear strength of the soil. How do you do that? I don't know. Planting trees, right? Root reinforcement. Or decreasing the driving forces. Now, the driving forces are all gravity, so you're basically talking about laying the bank back. Right? So here's an example of the kind of things we can do. So this is with the bank stability model. It's with an older version, but you can see this is the amount of toe erosion you would get if we had a silt toe, and in this case we eroded about 2/3 of a square meter from that cross section. Then you just simply change the material type along the bank toe, and you can see how the different type of erosion. So just in this example, we're now down to about 0.3 meters squared. Not saying that this is the answer, but this is what we can do and how we're going to analyze the data here in the Condamine. Give an example. I'm going to come back to the O'Connell. This is from Lake Tahoe, which is on the Nevada-California border. Same kind of thing. They're concerned about the delivery of fine sediment to Lake Tahoe, beautiful, pristine alpine lake. What this represents on the left-hand axis, stream bank erosion in cubic meters, so it's volume, okay, it's not mass. And each of these represents a site. So this is Blackwood Creek at river kilometer 1.94 under existing conditions and with toe protection, okay, whether it was rock or large wood or what have you. So the large numbers represent the number of failures that we modeled over this worst case annual hydrograph. They wanted to know worst case. So we had 7 failures. This is the proportion of material eroded by hydraulic action. The rest came from mass wasting, okay? So then we did the same runs, same flows, and all we did was change the toe material to rock. 1 failure. Now, this doesn't mean we're going to be this successful everywhere, okay? But this is the example of, even though hydraulic erosion only represents about 18% of the total erosion, when you protect that, look what you do to the total bank erosion. Okay, so just an example. So we want to account for root reinforcement. The model does that. We have root diameter here, tensile strength on the, actually that says tensile strength in megapascals. These are data from, mostly from North America. These in black are from the Australian species, and we are continuing to collect data. We just finished doing a Lomandra out here this week. And basically what this is showing that is the tensile strength relative to root diameter. Okay, so we can bring that into the model. This is data from Tom Hubbell's student at the University of Sydney, and they look a little different, don't they? They kind of plot differently, so we're a little concerned about that. But yeah, let me just leave that at that for now. So, but when we start looking about the effects, and this gets back to that original question, are Australian conditions different? And I think the answer is yes. The tree roots that we have, the riparian roots, go down about a meter and a half, except for some of the invasive species. The Australian species can go for almost forever, it seems, in some places. You know, Tom Hubbell and his guys have seen 5, 6, 7, 8 meters deep. And if you think about the effect of a failure plane having to slice through that root, that's going to make that bank stronger. It's going to make the channel narrower compared to an American one. So we look at this, we have factor safety on the y-axis and the age of the tree in years. So you can see how for this given hypothetical condition, and I don't remember what it was, maybe it's a bank 2 or 3 meters high, saturated, the effect of vegetation over time. So the North American species are plotted with the dotted lines, the Australian species are plotted with the solid lines. Okay, so you can see the value of repairing vegetation along Australian rivers. It's a 4 meter high silt bank. Okay, so coming on back to that, these are the modeling results that we had for the economy. Now, these are not final, they were preliminary. Basically, we modeled 3 successive bankful flows. So, with a bare bank, the total erosion at the crosshair is about 15.6 tons per meter, and then tons per meter per year, so we divided it by 3. And then we multiplied by the length of the channels that we knew would be unstable. This is preliminary, it's an estimate. We come up with about 39,000 tons per year under bare conditions. Okay? Andrew Brooks, he does a lot of work with engineered log jams. So we put in the cross-section for engineered log jams, increased the roughness, increased the critical shear stress of the material. And we found that we got anywhere between a 56 and a 75% load reduction. Okay, so in an applied sense, that's very good. And I suspect if we had modeled rock down there, it would have done the same thing. With mature vegetation, natural conditions, so basically we put 30-year-old trees on the top bank, we were down to about 9,000. Okay? So we went from 39,000 under existing to about 9,000 under natural. So what does that mean in terms of what we saw previously? The upland model showed about 16,000 tons per year coming out of stream banks, about 1.8% of the total. That's what we came up with. Okay? So it's an order of magnitude higher. Now, in terms of the exported materials, we were coming up with 39,000 tons were coming out of that system. Basically what we did is we multiplied the total load by the percent of silt clay, it was about 23, 24%, and then assumed that most of that material made it out. For natural conditions, the upland model said about 3,000 tons per year, 35,000. Okay? Now, this doesn't mean that these differences, it doesn't mean that this is truth. This was very quick and dirty analysis. This is an estimate. But it's pointing us to the idea that if we don't start thinking about channels and stream banks, we may get management strategies wrong. Okay, I'm rolling. Back to Alabama. Alabama. This is the Tennessee Tom Bigby River. This was a Corps of Engineers project to connect the Tennessee River to the Gulf of Mexico. Why? I don't know. Somebody needed some work. The idea was to connect the Ohio River and the Tennessee River so they wouldn't have to go all along the Ohio and up to the Mississippi and then on down. Okay, this is what it looks like. Okay, and the local management groups, much like Condamine Alliance, they're all concerned about, the agricultural folks are losing land. So what we did is we took a worst case annual hydrograph, we ran daily time steps, and we have the original bank in blue, and then checked what would happen over that first year of this worst case annual hydrograph if they did nothing. So that's the geometry. And then we tried various mitigation strategies. And this is what we're going to do here at Condamine. We're going to test different mitigation strategies, whether it's vegetation, whether it's rock, whether it's wood, whether it's laying the banks back, to see how these banks are going to change over time and what's the most cost-effective way of doing that. Okay, last one. This is a case study. This is kind of cool. This is really the only restoration project I've actually designed. I mean, I was a research scientist for 30 years. This is the place we're working. This is actually where we developed the bank stability model. But we had calculated that between the period 1966 and 96, over a period of 30 years, this meander bed had retreated about 15 meters, 14 meters, about half a meter per year. Okay? So, again, this was a research area. We had all kinds of stuff in the ground to develop the model. These were monumented cross sections. We had gauges on the main channel and a tributary coming in. We were sampling sediment. We were pre-SIP. This was 20 minutes from our office. After every storm event, we went out and resurveyed. Okay, so what it looked like in '99 to 2004. You can see, compare where the white buckets are, which are just 5-gallon buckets turned upside down, covering our tensiometers. That's how much it eroded over that period. You can see that the bend apex has kind of moved downstream. And in the upper right there, no, that's not the upper right, it's the upper left. that new bar there is not fluvial deposition. That's a bar formed from cohesive material falling off the bank, very good riparian tree sticking in there, and now it's a new bar, and it's going to kick the flows out. So, let me give you a little run through of what these cross sections looked like between May 96 and 2003. I'm going to flip through these quickly. The new profile is going to be the black line. Okay, so here we go. So the first event, we have some toe erosion, more toe erosion, bank fails. Okay, I'm just going to cycle through this. So you can see the bank moving, and on the opposite side, you see deposition going on. So this is a stage 5 channel. Bed's coming up, right? But the bank is still widening. Okay, so this is what it looks like over time. So between 96 and 2003, we're still eroding about a half a meter per year. There's another cross section. You can see how this bar is growing up. This is kind of the new stable, ultimately, this is the new bank full level. Another cross section. We do get out there in wet weather. Don't be afraid of the rain. There's our sediment sampling station. And you all have heard of Hurricane Katrina, right? So New Orleans is 6 hours south of us. We had 3 events the size of Katrina up where we were that year, 2005. This was the biggest one in April. Okay, so we used the bank model to model how we were going to stabilize this bank. And why did we want to stabilize this bank? Because the landowner, who had been letting us work there for a decade, ran for political office. And he won. And he marched into the area office and said, and we'd been paying this guy for leasing his land. We were paying him an order of magnitude more than the land was worth for any land that was lost due to erosion. But he wanted it fixed. So my boss came to me and said, do it. Okay. So I figured I would handle the geotech. I called my buddies at the Corps in Vicksburg and got their best hydraulics guy who handles that kind of stuff for that. We collaborated on this. Here were the issues. We had seepage. So we had infiltration coming through the bank. We had a less permeable surface, and it would run off, and we'd get kind of piping coming out. So that was one issue. The guy, and you saw a picture of that bend, he has a little farm road that comes across the top of the bank. We were not allowed to flatten that bank and get rid of that farm road. So, hey, client's always right. This is what I'm pretty sure you wanted. Okay, this is a Corps of Engineers project. Okay, they love the rock. They're all about the rock. So this is what they wanted. And actually, this project failed. It got. I'm standing on a county road bridge. 2 months later, this was all. It had eroded around the side of it. So I work with a guy named Dave Derrick, who is a very well-known guy in North America or in the U.S. with Benway weirs and longitudinal stone toe protection along the banks. This was his design. We can only bring the bank back to 1-on-1 because we had to protect that road. We only had 1.8 meters to work with. So we had to fill this whole area. So we went over to the bar on the other side, which had been grading, right? Pulled all that material in here. Dave brought along a geomorphologist that could drive a track hoe. You all know what track hoe is, right? It's those big things that grab stuff, take, right? That's really dangerous, having a geomorphologist with a track hoe. But this guy was a magician with this thing. He was literally picking up mature tree. He'd dig out a tree, he'd pick it up, dig a hole here, water it, slam the tree in, bury it, water it again, and these things survived. And I'll show you a picture of that. So the design was longitudinal stone toe to protect the toe of the bank, right, from undercutting. This Benway weir, which extends slightly upstream into the flow and basically kicks the flow out to the other side. Planted a hell of a lot of vegetation along here, roughened up the surface, left that guy alone, and let the river do its thing. Okay? Because all the measurements out there, we were very lucky. We knew how shear stress varied with discharge, right? So we knew the maximum shear stresses that we had to be able to withstand. Got online, Pierre Julien, Colorado State University. This is his spreadsheet for sizing riprap. This is, I'm sure, the things that engineers do all the time. I'm a geomorphologist. This is the first time I've used this. So I went through this spreadsheet. We figured out what size rock we needed, about 30 centimeter rock. Did an analysis of flow depths, the slope, and the critical dimensional shear stress, which is the kind of stuff you need to use to predict sediment transport. And we used the worst case. And that was what it said. We needed stuff up to about 57 centimeters, and so those were 2 mixed graded rock sizes that we used. Okay, so we checked that with the bank stability model, and we saw that we were going to reduce toe erosion by about 1/3 by just having rock extending about 1 meter up the toe. Okay. So The no action alternative is always an alternative, right? Because it's cheap, right? So we said, okay, here's our bank. We're conditionally stable. We're at 1.1. We're looking good. Water table comes up a little bit. We're unstable. All right, no action right now is not an alternative. But maybe, because that didn't fail 1.8 meters, which we had to go to his road, maybe we can survive one failure and just protect the toe. Okay? So we put the new geometry in, raised the water table. 1.44, we're looking good. Water table gets higher, still unstable. All right, we got to spend money. My boss does not like spending money. Okay, so now we said, all right, here's our one-in-one design. There's the geometry stable, we got 2.1, even with a drawdown condition, water table up. Still, when we get higher, unstable. Now we're sweating. In North America, Salix nigra, black willow, is a species folks love to use for stream restoration. I'm here to tell you it's great to reduce surface erosion. It is miserable for geotechnical stability. The roots are weak, there are not many of them, and they're all on the surface. So, willows, not good. River birch or sycamore are good, okay? So, we found that even with the worst drawdown conditions, we're stable. So this is basically the design we went with. Rock at the toe, with a lot of river birch and sycamore. Now, my ecology friends tell me, Andrew, never get up in front of a group of people and tell them you're going to plant a one-species culture out there. So I'm not saying that. So, and that's not what we did, but we made sure we had a lot of the river birch and sycamore. Because from our work on root strength and root depth, we know that that was the species we needed that would provide enough strength. So, January 06, and having the first, this is my first project. This took about a week to do, cost $30,000 over about 150 meters. You can barely see these Benway weirs sticking out here in the rock at the toe. You can't see it in the photo, but every piece of vegetation that was cut down from the other side was sliced and diced and planted here as posts, okay? And it helped roughen up the surface. This is that huge sycamore tree that was growing on that side that the guy slammed down in there. So this is 06 to 07. That's what it looked like right after construction. That's the up close of the Benway weirs. You know, so it doesn't look like this huge riprap project, even though we did rock. So this was a few months later. And you know, generally when you build a project, you get a 100-year event the following week. That's just the way these things work. Our case was that it didn't rain at all. And again, we were a research agency, so it was easy. We just sent a guy out and said, water the plants. Okay. We also put in a small rock drop to dissipate energy. Why? Well, we now have a surface that is smoother, right? We don't want to bounce that now stress off to the next bank downstream on the opposite bank and destabilize the next one. So we put that rock drop in there to dissipate the energy. That's what it looked like 2 years later. So, a fairly successful thing. 07 to 09, 07 to 09. Now again, because we were a research agency, we could actually go out and do post-project monitoring. Nobody ever wants to pay for that kind of stuff, right? They want to put it in the ground, see you later. So, pre-construction here, constructed, I like the earth tones, you know. So then we use this one. And so all the way through 2010, which is the last time we had surveyed it, you see that the bank had remained stable. We did get a little bit of scour, but it recovered and the bank was remaining stable. What happened with the plants? We not only used plants that we got from the site, but we also ordered plants from a company called RPM. I'm sorry, I don't remember what that stands for, but they're from St. Louis. But they get their plants and they tend to generate their roots very, very quickly. Okay? Because once you put that plant in, that doesn't mean you get the full benefit from it as soon as you put it in the ground. It takes time. And from our work in North America, 3 years. That's a long time. Okay, particularly here in Australia, where you've got the wet and the dry. You've got to be able to handle the wet. Okay, so at the end, we had about 50% of the plants that were actually, because they were tagged, that we were able to find, or another 25% that we couldn't find. That we like to think were probably still there. Bed material. We went from a gravel bed stream, about 12 millimeters, down to a sand bed stream from all the construction work, and within about 6 months to a year, we were back to a gravel bed stream. And this just shows the percentage of sand and gravel. So we hadn't really disrupted the system. So ultimately, that's what it looked like in '97 when we first got there, and when we left, that's what it looked like. And that should be, I'm going to call it a day. Should we call it a day? Well, no. This is yeah, we're going to call it a day. Okay.
We have 10 minutes for questions if there's
Okay, yeah, I'm sorry. I'm a New Yorker, you know.
I'd just like everyone to thank Andrew for his time. And this is part of what is a 5-day intensive course. So for Andrew to cut down
Yeah.
to an hour and a half is quite an effort. So, and I have sat through the 5-day intensive course, and it's some really fantastic stuff. And the best analogy I can think of is, does anyone at all follow the UK chef Heston Blumenthal? He applies a lot of scientific approaches and measurement to cooking, and he uses temperature and measures rather than and weights rather than cups and whatever. And the whole fundamental idea of his cooking is that the difference between a good custard tart and a bad custard tart isn't luck and skill. It's the physical properties of the ingredients that you're putting in that custard tart and the physical forces acting on that custard tart. So if you can replicate those every time, if you can have the same ingredients and the same temperature or whatever acting on that for the same time every single time, you'll get the same custard tart every single time. And bank stabilisation isn't about a magic black box of we'll put the riprap in and see if it works. If we can understand the physical properties of the material we're working with and the physical forces acting upon those materials, we can increase, we can make
that custard tart.
We can increase our chance of success in banks restoration and stability work. And it's about the science, getting the science right, and the science underpinning the management. So thank you very much, Andrew, for your time.
You're very welcome. Thank you for
and
sitting.
let's open up to some questions.
Cyril.
I suppose I should ask a question.
I'm not surprised.
I thought you could have said more about looking at where the channel lies in terms of this longitudinal sequence, both in like distance and time.
Mm-hmm.
We come along at time and we see the erosion at this, bad erosion at this point, we come along 20 years later, we find it's up the valley further. You did mention some of that. Could you tell us a bit more about that sort of approach?
Yeah, sure. I mean, it's the idea of the rapid geomorphic assessment is that it is is somewhat time dependent as opposed to time independent, which a lot of the classification schemes are. Granted, it's a shot in time, right? You're out there, you're looking at it, but it's giving you an indication. For instance, if you have a channel that has downcut and now the banks have started to fail, okay, you know that at that site over time, okay, assuming that this thing is migrating upstream, that's going to continue to fail, right, until it fills up enough or the channel gets wide enough that the stresses are not great enough to undercut the toe. So, I mean, it's a very good point you bring up. There are two issues. How does it change at a point over time, and how does it change over time, or at a moment in time, longitudinally? Now, if you're asking the question of how long does that sequence take, I'll give you the good government researcher answer. It depends. You know, it depends on the materials. So, for instance, if you have a coarse grain system, right, it's going to heal itself much quicker because that sediment is moving. It can get deposited faster. The bed can come up. The banks can move out quicker and reduce those stresses. Cohesive systems like this one will take longer to respond because you don't have that hydraulically controlled sediment. A lot of it, once it comes up, it's going to start moving right through.
I'm thinking in terms of like these clusters of wetter years. You'd see like, I think episodic changes moving back through the system.
Yes, I would think so.
I think that's one of our biggest problems here, that we haven't appreciated that sort of thing.
Well, I mean, I think, you know, Stan Shum, who is my PhD advisor, he kind of addresses that. You know, so instead of like in a humid temperate environment where you have this semi-nice, smooth, nonlinear decurve, here in Australia you might have what Stan called, and I don't know, it was a crazy term, but it would go down and then it would stop, and then jump down and stop.
Static dynamic equilibrium.
There's like metastable or some blah blah. Yeah, yeah. It was some term that is completely unimportant.
It's
but
like had two opposing ideas. Where it was stable, yet it was dynamic. You know?
Yeah. Well, basically, what it was showing is that so in the example where you have these wet periods and the dry periods, just like with St. Helens, where you have that, on the one hand you can draw that nice linear curve or nonlinear curve, But then in a couple of places you have this thing going on, then you get that next lahar, which kind of kicks it. But it's still set up by the original disturbance. Okay?
Yeah. Thanks.
Mark?
Yeah, at Connell River, were you more or less saying that the previous estimates of bank erosion were probably way under?
Yes.
And
I'm saying that our value is also an estimate, though.
yeah.
I mean, that is not something that I would write in a journal.
So what was the quantum compared to the total estimated load? What sort of percent would it be?
I don't know, it depends, I don't know, remember off the top of the head what the total load was from SEDNet or source, I don't know which one. Was Brody 03, was that SEDNet or source
Yeah,
catchment?
SEDNet.
It was.
We also think that it may have been overestimating hill slope, so there's probably some sort of a balance there as well. So
Yeah.
it's severely underestimating bank and bed, but it's overestimating hill slope as well. So
Yeah, so
somewhere
ultimately,
in the
you may
middle.
get close to the right answer down here, but when it comes to like then defining management strategies, and Andrew has done, and he's talked to Scott Wilkinson about this. We were in Canberra at a meeting together, and I had to talk, Andrew had to talk, and Scott had to talk. It was really unfair, and for Scott. And we, but Andrew's work up in the Normanby, particularly with regard to gully erosion, is showing that gully erosion, and we talked about this yesterday, that gully erosion was the dominant thing, and then he showed some very convincing arguments that if he had utilized, in terms of sediment budget he was developing, if he had used the output from SEDNet to estimate upland erosion, okay, in his soil plots, it would have meant amount of sediment. He had a photo of the soil plot and his son standing in the middle of it, right? And it was, basically they collected about that much sediment in that over the year. And the analogy was that if the SEDNet value was right, it would have been a mountain of stuff in that area. So, and it was orders and orders of magnitude overestimating, it seemed. And what we saw in the O'Connell, for instance, Andrew knows much more about the Normanby, but the O'Connell, again, we drove around that basin and it looked pretty good in terms of the uplands. And so it was hard to imagine how a basin that size can be producing, 750,000 tons per year of sediment with only 1.8% coming out of the banks. But again, our work is just very preliminary.
There's SEDNet too, and there's an old National Land and Water product. The satellite interpretation missed the mark, didn't count dead grass.
Mm.
So Andrew and co have been sort of looking at that, and I'm going, well, it's rubbish. Don't even look at it.
Right.
So,
Mark, as you and I talked about yesterday, I think a lot has to do with just communication. And to a certain extent, it may even have to do with personalities, and the personalities being able to communicate with one another. Because I think we're far enough along, we understand the science. We understand what we need to do. It's just a matter of doing it now.
I've got one, just bearing in mind your worldly experience, what's your gut feel of the Condamine, what you've seen in the last...
I like the Condamine, it's cohesive.
So are we doing the right thing, actually
Well,
stepping into the interference and...
It's funny. I woke up this morning and I've had 2 interviews, one on a radio and one on TV, and I'm really uncomfortable in those situations. And so one of the first questions they asked was, so, what are your recommendations? It's like when you come out to a field site, right? And somebody's invited you in, and you get off a plane and you drive up to the site, and people have been there for 20 years, right? And they go, right, Dr. Simon, what do you think? And what I've learned is to be quiet at those moments. But that said, and I will tell you what I told Sophie, I guess the TV interviewer. What I saw out there was for a system, okay, so let's talk about the uplands first. For a system that just gotten pounded, right, by a couple of huge events, it seemed amazingly resilient to me. If you're expecting not to have gullies after events like that, you're nuts. I mean, you're going to get them. Human beings are on the landscape. There are even natural processes that are going to cause those things to happen. But by and large, and we drove a lot. I mean, I have no idea how many miles we put on that rental car. I was expecting to see scars You know, I was expecting to see scars up high, you know, debris flows. I was expecting to see gullies off the pediments and the foot slopes. You didn't see many of them. When I looked at the main channels, and I didn't look at a lot of them, Glengarran, okay? When we, a couple of gullies we were looking at, or one of the gullies we were looking at, draining to that, and then to the Condamine itself, yeah, it looked like a huge flood had come through. But it held in there. You know, the Condamine at St. Ruth's Reserve, I guess was the area we were looking at. It looked like a huge event had come through. I mean, we looked at high water marks, 3.8 meters high. It's a big, big event. But the trees were still there. Yes, there was some bank erosion. It's a natural process. So the first take-home message I got was that, okay, it's not as bad nearly as I expected. Second take-home message from the data we've collected and what we've worked up so far, the soils are very cohesive, which is good for bank stability, right? This is Australia. Things germinate and grow and transpire 12 months a year. It's not like us. We've got 6 months with, or 3 months with stuff doesn't grow. So planting vegetation is a good thing. I think the landscape looks good, and I think management of this landscape is completely viable. I don't see a lot of what. It's a question the radio interviewer asked this morning. You know, what do you see in terms of bad land practices, basically? And I didn't. You know, it looks good, and that's a testament to you folks on the ground. And I always say that my job is easier. I was going to use another term. My job is easier than your job is. My job is to do the science, and this is what we do. I mean, we've done it all over the place. Implementing these things on the ground and working with, sociological and political issues are always, I think, more challenging. So I think you're in really good shape here.